Hey everybody, today we're going to be learning about periodic trends, which is essentially talking about the patterns that occur on the periodic table. We know a lot about the periodic table when we look at it, the symbol and the atomic number and the average atomic mass, but we've also learned over the years other patterns that show up because of how the table has been laid out. And we're going to talk about those things today. So first, a real quick review. You did an activity with Coulomb's law in your last homework assignment. And essentially what this is saying is that attraction, so the positive and negative attraction of protons and electrons is directly proportional to the size of the particle and the distance of the particle. So the larger the particle, the stronger the attraction. So in other words, something that has a lot of protons in it will have a pretty big pull on its electrons. But we also know that the distance between the proton and the electron matters. So the shorter the distance, or the closer they are together, the stronger the attraction. And that makes sense. If you think about a magnet, if you get them really close together, they will eventually pull into each other automatically. So larger or more protons have a strong attraction, but also the distance makes a difference. And these are going to kind of be woven through our different trends today. So the first one I want to talk about is atomic radius. And atomic radius is how large an atom is. And so the definition's up here, defined as the distance between the nucleus, which is the center, and the outermost electron, right? So again, that's the middle, or the nucleus, to its outermost electron. So a smaller atom has its electrons that are closer to the nucleus. A larger atom has its electrons further away. And what we know about this is that as you move across the periodic table, so going from left to right across the periodic table, we're adding protons to the nucleus, right? So if you take a look at this periodic table here, I've got lithium, which has 3 protons, beryllium, which has 4, boron has 5, and so on, going across. So as we go across these periods, we are adding more protons. And we are staying within the same energy level. So if I go back to this example, this is energy level 2 right here, right? So all of these are in the second energy level. So we're adding protons to the nucleus. We're adding to the same energy level. And so we say that atoms get smaller from left to right. And this is why I highlighted in yellow. So if you have more protons pulling on the electrons, but they're located in the same level, that's going to cause the electrons to be drawn in more tightly. And if you draw in those electrons more tightly, you have a smaller atom. Okay, so I'm going to say that again. If you have more protons in the same energy level getting added, they're going to pull the electrons in more tightly, and therefore atoms get smaller from left to right. So lithium is going to be the biggest atom in this period. So beryllium is smaller, boron is even smaller, carbon is even smaller, and as you go across, you're staying in the same energy level, adding protons, pulling those in. So neon is the smallest element in the second energy level. Okay? So let's talk about the size of an atom as you go from top to bottom in a group. So if I look at my periodic table here, if I go down this first group, the alkali metals, we start with hydrogen, and then we go to lithium and sodium and so on down the line. The difference here is we're not in the same energy level anymore. So hydrogen's in the first energy level, Then we have lithium in the second energy level. Sodium's in the third. So essentially, we're adding and getting further and further and further away from the nucleus because we're adding an energy level. So atoms get larger as you go down a group. So going down a group, principal energy level increases. So that means we're adding an energy level, and that makes the electrons further away from the nucleus. Okay, so that's our size trend. And here's a little visual to help you guys a little bit. So from top to bottom, you have increasing atomic radius or increasing size. And then from left to right, the size decreases. Or in this case, it's showing you it increases right to left. Okay, so this is super important that you understand this trend because this is related with the other trends we're going to talk about today. So trend 2 that I want to talk about is ionic radius. So just a couple of reminders here. An ion is an atom that gains or loses electrons to give it a charge. So when it gains electrons, it's negative. When it loses electrons, it becomes positive. So keep that definition in mind, and if you need to go back and review that from the last unit, go for it. So when we're talking about the trend for ions, we're going to compare its neutral to its ion. So in other words, if I take a look at sodium, right? Sodium is number 11 on the periodic table. Sodium has one valence electron, so it tends to lose that electron in an ion, and therefore it becomes a positive 1. Okay? So we're going to compare sodium as its neutral self to its ion, which would be a sodium plus 1. So we know positive ions always become smaller. Okay, and this is how we can kind of explain this. If we stick with our sodium, I'm going to add a little text box here. If we stick with our sodium example, we have sodium normally has 11 protons, and 11 electrons, right? Our sodium ion, we said, was a plus 1. Our sodium ion has 11 protons, but we said it lost an electron, right? It tends to lose that electron and therefore becomes a plus 1. So now we only have 10 electrons. So this is what we want to compare here. Let me make this a little bit bigger. And let's change its color. Okay, so if I have my neutral with 11 protons and 11 electrons, but my ion has the same number of protons, the same number of pluses, but it only has to pull on 10 electrons, it's going to have a stronger pull. Okay? So 11 protons on 11 electrons, think of it as a tug of war. So you've got 11 people on both sides pulling. So this neutral atom is getting 11 and 11. If you suddenly only have 10 electrons on the other side, these protons are able to pull that in towards it. And so our positive ion always is smaller than its neutral counterpart. Okay? And then again, the highlight is to help explain that. So we're losing electrons, we eliminate that level, we get pulled in tighter, the ion is smaller. So if we look at a negative ion, so let's take a look at chlorine. Okay, so chlorine is over here on the right side of the table. I've got 17 protons. So if I do the same thing, and let me just do this to save some time. So we're going to do fluorine. Right, no, I said chlorine. So I've got chlorine. And chlorine becomes a -1. And chlorine, we said, had 17 protons and 17 electrons. So chlorine has these 7 valence electrons here, and so chlorine tends to gain 1. So if I gain 1 electron, I'm now going to have 17 protons and 18 electrons. That gives me my -1 charge. So take a look at the difference here. Think of your tug-of-war game, right? 17 with 17, pretty equal pull. With my ion, the 17 has to pull in 18. It's not going to be as strong of a pull towards it. And so therefore, the neutral atom is smaller than the ion. Okay? So the ion is bigger, neutral atom is smaller. And this is, again, explained here in the highlighted area. So maybe just pause the video and read that over and make sure that you understand what's going on here. Here's a little visual. So here's your positive ion is smaller than the neutral. And here your negative ion is larger than the neutral. And then the next slide is another just visual. Sometimes you'll see this online. The army green would be the neutral element, and then the red is the ion. And on the right side here, the teal is the ion. So you can see the ions are bigger for the negative, but they're smaller for the positive ions. So just a couple different visuals for you guys to look at for that trend. Okay, we have a couple more to go. So our next trend is called ionization energy. So the definition is that's the energy required to remove an electron from an atom. So that I have to pull that electron away from the pull of the nucleus. Okay, so we have to think how strong or how tight is that being held? And if it's being held really tightly, it's going to take a lot of energy, right? So these atoms that have the electrons pulled in real close, real tightly, that's going to require more energy. So you can think of it as the smaller the atom, the higher the ionization energy, because it's going to take more energy to pull that electron away. So if we look at the periodic table from left to right, remember in our first trend we said electrons are tightly held going from left to right. So the amount of energy it's going to take to remove that also increases from left to right. Okay? So, and actually I'm going to take this off. You don't need this. Ionization energy is going to go up, more tightly held. Therefore, it increases from left to right on the periodic table. If we think of from top to bottom, up towards the top and then down a group, it's going to decrease. So the amount of energy goes down as you go down the periodic table. Because remember, we're adding energy levels. And if we add energy levels, the electrons get further and further and further away. And therefore, it's a lot easier to pull off the electron. So ionization increases from left to right, and then it decreases from top to bottom. Or in this case, they're showing you increases bottom to top. Okay, again, this all relates back to the size of the atom and how close those electrons are being held. Electronegativity. So this is thinking of not pulling an electron away, but this is how likely an atom is or its ability to attract an electron. So this actually has a numerical scale, and it goes from 0.8 to 4.0 on the Pauling scale. There's a couple different scales that are used. We're going to use Pauling's. So the larger the number, the more likely the atom is to gain an electron. So again, these are going to be your smaller atoms close to the nucleus because that's going to attract your electron. Okay? If it has a small number, that means it's a lot less likely to gain and more likely to lose an electron. So let's go back to our periodic table and say, which side of the table here is more likely to have a high electronegativity or a high likelihood to gain electrons? And that's going to be over here on the right side. So something with 6 or 7 valence electrons, remember it only has to gain 1 or 2. These are your high electronegativities, most likely to gain electrons. And in fact, fluorine's the highest because the electrons are closest to the nucleus. It only needs 1, and therefore it's going to pull that last electron in very, very tightly. Elements on the left side of the periodic table generally don't gain electrons. They're going to lose. So these have really low ionization, electronegativities. So these guys are less likely to gain electrons. They are more likely to lose. So they're going to have a low electronegativity number. Okay? So the larger the number, the more likely it is to gain. The smaller the number, the more likely it is to lose. So let's look at our trend from left to right on the periodic table. Electronegativity increases. So it's more likely to gain that electron because it has a stronger nuclear pull, right? And that has to do with the size. Because they're getting smaller, the likelihood to gain gets larger. Going down a group on the periodic table, we're adding an energy level every time you go down the group, and so therefore you have less of an attractive force from the nucleus. So that means it has a lower electronegativity, less likely to gain. So here's your little visual. So from left to right, we have an increasing electronegativity, and from top to bottom, it decreases or increases bottom to top. And the very last trend, we're not going to spend much time on, it's electron affinity. It is very much the same as electronegativity. So it's the likelihood of gaining an electron. Again, the left side is low, the right side is high. Just know that this is the definition for it. So a lot of times electron affinity and electronegativity in high school are used interchangeably. The thing that's nicer about using electronegativity is that there's a number connected to it, right? So there's a quantitative value that we can use to actually compare one element to another. So we tend to use electronegativity as the trend when we're talking about gaining electrons. So those are the trends that we are going to be using. And I would like you now to go and do the trends graphing activity that is located in Canvas for you. I hope these notes help you, and we'll see you soon.